And again, today's material is also going to be on the exam. And yeah, so there's one more thing I want to show you guys. It's called the method of transformation. So on Tuesday, we have seen something like the probability of x and y is equal to the probability of x conditional on y multiplied by the marginal of y, okay? And we call this the joint distribution or the joint probability. And the probability, again, is coming from the density function. So it's coming from the joint density function. So you will need f of x and y to calculate the probability for p of x and y, okay? And then we call this the conditional probability. And then this one, the marginal, okay? So this is under the conditional thinking or the conditional probability regime. Maybe I just put the thinking as a high-level conceptual thing. Okay, so the idea is that we have the conditional multiplied by marginal, we get the joint. And this is when the x are conditional on y or vice versa. There's some dependency there, which is what when we introduce the conditional part. Okay, but when things are independent, just like coin tosses, then we will have the joint probability just equal to the product of the two marginal. So we have also seen some instance when we're calculating the moment generating function of x plus y, when they are independent, usually you will have the product of their individual density function or moment generating function in that sense. So all you need to do is just multiply by the two marginals. Okay, so today we are going to focusing on manipulating or handling the joint density function, and also by seeing some transformation. Okay, so yeah, one more intuition is that earlier or before today, we have been working on random variables that are composed of other random variables, such as in the homework or in the practice midterm, you have seen that I was asking, we have a route A and a route B. I'm asking for the difference of the two routes. So you take the difference of x minus y. And then you're resulting in a new additional or single variables. And then you calculate the marginal probability using the normal, and then you find out the probability quite large, and then you can make some decision there. Okay. So for today's interest is that we are talking about the joint. So instead of taking the sum or difference, let's say the sum of the n random variables or sum of the two random variables, we're focusing on talking about two that they are jointly in the density function instead of taking the sum of x plus y. We're focusing on the density function of x and y. Okay, so previously we talked about the probability, or in the practice midterm, we have something like d is equal to x minus y. So we are interested in the marginal of the density for d. But this time, so for today's lecture, I'm going to talk about the joint of the two instead of taking the difference or sum. And you will see there are two in the parenthesis instead of a single variable showing up, where the single variable is coming from the two. Yeah. So we are focusing on this one. Okay, so now let's introduce the idea of the transformation. So let x1, x2 be random variables with the joint density function. So now, instead of putting one variables inside the parenthesis, we need to put two random variables. So here, let me also, because just for clarity, so now let me just add one more subscript. So let me put capital X1 and capital X2 at the subscript to referring that this is the density function referring to X1 and X2. Later, after the transformation, we will transfer to something else, and then I will put different letters at the subscript. So now I added one more subscript to referring the subjects that I'm working on. So I'm working on X1 and X2, okay? And then again, in the density, in the parenthesis, you need to put the variable of interest. So here, usually you can put lowercase x and y, x or letters in the parentheses. So maybe let me also make it more. Okay, and then lowercase x1 and x2. So again, just to make the clear, is that previously we are working on, let's say x, we have the lambda equal to e of negative lambda. So this is the marginal density for the exponential distribution. But for today's lecture, we are going to focusing on the joint, which is related to the Tuesday's material where we have the joint. And then today we are also going to focusing on the independence regime, okay, for simplicity. But the difference is that earlier or before today, we're talking about the marginal, only one variable in the parenthesis, and today we're focusing on two variables inside. Earlier, we have also worked with two or more, but we're taking the sum or difference or some scaling factor. That is also different. So today we're going to focusing on the joint of two variables. Okay, so just to say something more to make it clear. Okay, so here we have two random variables with the joint density function f of x1 and x2. Suppose we are interested in two more variables, or we are interested in two more quantities. So let me first write everything down and then I will provide more explanation. So now I'm interested in y1, and y1 is a function of the two variables. So here I put g1 and then input x1 and x2. Okay, and then I'm also interested in another quantity because we are working on joint distribution with two variables. So here we also are interested in two variables of a transformation of the x1 and x2. Okay, so here we write y2 equal to a function of g2, x1, and x2. Okay. Now the question is, we want to find f of capital Y1 and Y2 in the subscript, lowercase y1, y2. Okay, so we want to find the formulation or the density function after the transformation. Okay, so this will be the context for today's focus. Any question for the configuration right now? Okay, so now let me first provide the formula to handling this, and then we will look into examples to applying this. And if time or maybe in the Tuesday or in the next week, I'm going to show one more thing, which is called a T distribution, which to me is extremely important in many of biological studies. When you are doing experiments, you have like a treatment A, a control group, and they want to test their difference. And I'm pretty sure you guys are all doing t-tests. It just maybe you are not familiar with the mathematical things in the back end. But after the transformation, I will show you the mathematical. So I will show you the mathematical derivation, and maybe that will give you a more understanding on some of the t-tests or analysis you do in your experiment or biological studies, something like that. Okay. So now let me just provide the formula for the transformation. So first, let x1 equal to h1 inverse y1 and y2. Okay, so here the h1 here is called the inverse function. So the main difference from, let me first write down the x2 as well. So x2 is just the inverse function inputting y1 and y2. Okay, so the inverse function is inverse with respect to the g1 and g2. So here, the transformation of interest, we write it as y1 equal to a function of x1 and x2. This is saying you input x1 and x2, you will get something, you will get y1 on the left-hand side. And then for the g2, when you input x1 and x2, you will get y2 on the left-hand side. And the inverse function is saying, when you input y1 and y2 on the right-hand side, you will get the x1 itself back on the left-hand side. And the inverse function h2 is saying, when you input y1 and y2, you will return a x2 on the left-hand side. So it's the inverse is with respect to the g1 and g2. So g1 and g2 is that you input x1 and x2, you will get y1. Input x1 and x2, you get y2. The inverse is saying when you input y1 and y2, the things that you transform into this function, you will get x1 back. And then for that one, you will get y2 back. So it's inverse in a reverse direction. You input something, you get the original things back. So the original is x1, x2. We are interested in some transformation of the x1, x2, which we define as g1 and g2. And then the inverse function is that when you input the thing that you transform already, you will get the original thing back. So that is the inverse it's referring to. Okay. So here the thing that I write is -1. So usually they write -1 as the inverse thing. So in the fraction, it's like 1 over something. And then for the function, it's referring to the inverse function. Okay? The idea is that you input the thing that you already transform, you will get the original thing back. So you will get x1 and x2 back. Okay? Okay, after you have rewrite or you have the inverse function, then there's one more thing you need to calculate. So let me first write everything down and provide the explanation. So here, you need to take the derivative of the inverse function. Here, with respect to the things that you already transform, okay? So here you have the, okay, first of all, this will be a kind of like a table. So on your notes, please make sure you leave some space. So I'm going to fill in 1 entry, 1 2 2 2 entry, 1 2 1 entry, okay? So make sure you leave a space, but yeah. And later I will add some more things on the outside, but make sure you have some enough space as a table. Okay, so the first entry is that you take the inverse function and then derivative with respect to y1. Okay, on the 1, 2 entry, the second column on the first row, you take the derivative of the first inverse function, but now with respect to y2. Okay, so that means so for the rows, you are working on the same inverse function. So if you have 2 inverse function, you will need 2 rows. If you have 3 inverse function, you will need 3 rows. Okay. And then for the 2, 1 entry, the second row, the first column, you take the derivative of the second inverse function. So here, notice the notation subscript here, the 2, that this is the second inverse function. Taking derivative with respect to y1. Okay, and then for the 2, 2 entry, second row, second column, derivative of h2, the inverse function, y1, y2, d of y2. So derivative with respect to that. So again, earlier I was saying, the inverse function is that when you input the thing that you already transformed, and then it will return the original. So the inverse function is a function of y1 and y2. That means you are allowed to take derivative with respect to the things that are input of the function. Okay? So if the input is not at y1 and y2, there's no need to take derivative, it's just 0, right? So now h1 and h2 are the inverse function which take the input of y1 and y2, so you are allowed to take derivative with respect to the things or the input of those functions. So you are able to do that. And now let's do one more thing. So it depends on your notation. So if you, up to your notation, if you want to write it explicitly in the math, you can write it as determinate and then inside the parenthesis. But for if you look at some other mathematical textbooks, people just use a large vertical line to refer the determinant of this. Have you guys know or worked with a vector or matrix before? Yeah. Okay. Yeah. So matrix is just you packaging. It's just a nice way to packaging everything into rows and columns, just like an Excel sheet. And then the one-dimensional case is just called a vector. So vector and matrix is just a compact way to packaging things for mathematical operations. And here we actually have a 2 by 2 matrix, and then we can calculate the determinant. Okay. And then we call this determinant, we give it a name called J1. And the J is stand for Jacobian. Okay. So when you take the transformation, usually you need to calculate, this is called the Jacobian matrix. You take the determinant of the Jacobian matrix. So that is where the J is coming from. Okay. And then one more thing for the formula for the determinant is that if you have a matrix of A, B, C, D, then the determinant is just the AD minus BC. Okay? Only for the 2 by 2 case, okay? For now. Yeah. We're talking about two variables at this time. So this is the determinant for the 2 by 2 case only. For the when you have talking about joint of lots of things, determinant. So make sure you look up the determinant formula. Okay. But for the 2 by 2 case, that is the one that we will use. So the diagonal minus the off diagonal. Any question up to, yeah? A little bit more? Yeah. Keep going? Here? Keep going? Yeah. Let me know it's good? Can I, yeah. Can I scroll down now? Yeah. Okay, good. Yeah, maybe I'll pause here. Yeah, any question or comments up to this point? So up to this point, you do formula things, get the corresponding component, doing some operations. These are just the formula.
You're going to be evaluating those derivative functions at y1 and y2, right?
Yes. Okay. So later you, in the examples, or here is already saying that this is the input of y1 and y2. It's a function of y1 and y2. So we're taking derivative with respect to the input of the function. Okay. Any question before we proceed to the... Okay. Once you're calculating that, then again, back to our question. We have two random variables. We know the joint from the original is the y1, x1 and x2. We are interested in the function, the joint density function of the y1 and y2. So we're interested in the density function of a different subject. Okay, this is the thing that we already have. We are interested in some transformation, so the density function of the new subject. Okay, once you have the Jacobian matrix, you can get it from the following. So f of y1, y2, whose input is lowercase y1, y2, is just equal to the density function of your original x1, x2, but by replacing the x1 with the inverse function, with the whose input, so the inverse function, the input of the inverse function is still y1 and y2, and now we are replacing the x1 to the original density function with the x1 in terms of the y1 and y2. And then by replacing the second one with the inverse function here. Okay. After you replacing the x1 and x2 inside the original density function, there's one more thing. You need to multiply by J1 absolute value. So the J1 for now will give you a scalar, and here the two vertical bar is saying the absolute value. Okay, once you perform all those transformations, you will get the density function for the new subjects. So So one example could be still, maybe we can still use the context of the midterm, practice midterm 2, where we have two routes transferring from point A to point B. We have route, let's say from the 2 points, we have route A and route B. So in practice midterm, I was asking for the single, So in the practice midterm, I was asking for what is the probability, or I first asking you the density function for the D, where D is the difference of the two routes, okay, right? And then you derive it through the homogeneous function, and then you find out the function for the difference is a normal distribution. Okay, so now I'm asking you, in addition to the difference of the two routes, I'm also asking, let's say, another letter, maybe I'll ask S, which is the x plus y. And now I'm asking you, what is the joint density function of both the difference and the sum of the two routes? And that will be one example for the usage of the transformation. So the transformation is that instead of talking about one, we're talking about two, and then we are also talking about a transformation of the original variables. So in practice midterm 2, we have the number of the minutes for route A, the minutes on the route 2. But now I'm asking the density function for the difference of the route A minus route 2 and the sum of route A plus route 2. And then their joint density function, what does it look like? And that question will be answered by the transformation here. So actually, when you take the D equal to x minus y, that is also a transformation. So back then, we already working on the transformation. But that is a transformation of a single variable. Now we're talking about transformation of multiple variables. You will need to calculate the Jacobian and then implementing in this formula here. Any question up to this point? Okay. So now you have the formula for performing the transformation. Let me just introduce one more formula, and then which is doing the same thing. So let me introduce J2. Okay. Again, it's a Jacobian matrix, and then leave some space for the 2 by 2 entries there. Okay. So J2 is also calculating with the derivative for each component, but this time let's start from the original transformation, G1. So G1 has the input of x1 and x2, so now you will need to take derivative of x1 and x2 with respect to x1 and x2. The second entry here is d of x2. So again, the first row is using the g1s, okay, but taking derivative with respect to x1 and x2. For the second row, you take the derivative of g2 dx1 dx2. And then again, depends on your preference. So if you do the vertical bars, if you're looking at, if you're reading some mathematical textbooks, the vertical bars for a matrix is referring to determinant, which is the same as this notation, the determinant notation. It's just depending on your, on the author's preference. So again, this is also another notation for determination, for determinant of a matrix. And we call this J2. Okay. So once you calculate the J2, you can still use the formula here. So maybe let me put it here. Once you have the Jacobian matrix J2, you can still use this formula, but slightly different. Okay. Instead of multiplying by the absolute value of the J1, you can still multiply by the absolute value of the J2. But this time, don't forget to put an inverse. Okay. So this is saying if you have 5 inverse, this is just 1 over 5. Okay. So if you choose to use J1, so the J1 is coming from the function after the transformation. Like you're interested in the difference of the two routes or sum of two routes, then using the function after the transformation. If you choose to use J2, that is the original the opposite direction. So G1 is G1 is referring to the after transformation. So you transform something into a new variable. So all the G's are the after the transformation, and the H are referring to the inverse function. Okay, so just to make sure that when you're starting from H1, that means you are using the J1, using this formula, multiplying by the absolute value of J1. If you start from the transformation, then you are obtaining J2, and make sure you take the absolute value and then the inverse of that scalar. So don't forget you have an additional inverse. So the two formula will both give you the new density function of interest. So it will still give you y1 and y2. Then the question will be which one to use, maybe. So it really depends. If your transformation is very complex, and then if you are able to obtain the inverse, and then the inverse is easier, then maybe use a J1. If the transformation is already relatively easy, then, or easy in terms of that you can take the derivative easily, then maybe you can start with J2. So it depends on whichever is easy. Just like when we're calculating the expectation, you have multiple ways. You have the integral ways, you have the homogeneous function ways. Which one to use depending on which one is easier. And then you can choose and then get the new density function. Okay, any question or comments up to this point for the formulation before we proceed to the example? So these are just the formulas for generic letters, functions. Yes.
In the example you didn't go over, and like in future homeworks and assignments, when we have a question like this, will it also be symbolic, or will it be like numbers and we get actual? Like,
It will be more like the example I will show.
okay.
Yeah. So this is the formula. So I'm using generic G1, H2.
Okay.
But I will give you the actual G1 and G2.
I see. Okay.
Just like in the practice midterm 2, I was saying the difference of the two routes,
Mhm.
right? D is equal to X minus Y. And that is the G1, one transformation.
Okay.
Yeah. So again, the idea is that we know the two routes, the travel time follows two normal distribution. But instead of interesting on the traveling time, let's say the company is interesting on the difference to make a decision. If the difference is too large, then I probably want to go to the routes that is shorter, right, taking less time. And then in the practice written 2, I was asking for the probability, and then you find out it's quite large, right? And then from there you can make a decision that maybe we should switch to route 2 because route 2 is faster. So that is the difference, the information that the difference can provide. And now I'm asking for a more deeper question. What is the density of the joint? And then from the joint, you can also calculate the probability, and then maybe you can answer some more complex question. Any other question, comments regarding the formulas? Okay, if not, let's see an example. Okay, so now let's x1 following an exponential distribution with parameter lambda 1. Let x2 also following an exponential density function with lambda 2. So we have two variables, and then we know their density function. And then also x1 is independent of x2. So different from the case on Tuesday, where x1 depending on x2, which is, it could be very complex, like the ChatGPT, which is the conditional case. But here, for simplicity, let's now focusing on the independent case. So the independent, and the x1 and x2 are independent. Now, let's say we're interested in the following two transformation. We're interested in the sum of x1 plus x2. So in the context of that routes, that is the sum of the two routes. So maybe instead of, so you have the route A and the route B, you're going there, coming back. So the sum will be what is the number, what is the minutes, the sum if you go from route A but come back to route B. So that could be the sum. And then maybe the company is thinking, if I go to route A but using route B to come back, maybe I can avoid traffic. So maybe the company is interested in that, then the sum will be interest. And then the V will be x1 minus x2. So maybe these variables can help the company to decide whether I should choose route 1 and route 2. And then that is the example in practice midterm 2. Quite high, so you want to using another route. Okay, so let's say I'm interested in the two transformation, x1 plus x2 and x1 minus x2. So the question is, find the joint. So now let me write, let me write capital U. So if you want, it's just really a preference thing. So whether you, so usually for random variable, people write capital letter, and then for the input of the function, they write lowercase. Okay, but it can be not that difference in terms of how I write in for the penmanship. Okay. So we're interested in the joint of the u and the v, again for x1, x2 independent. Okay. So this will be a very typical question, or just an example for the method of transformation. So any thoughts on how to implement the method that I just introduced to solve the problem here? So what do we need and how to proceed? So let's say this is the variable describing the travel time for the two routes by using exponential distribution now. And now I'm asking for what is the joint density function for the sum of the two routes and the difference of the two routes. Or even for stocks, like what is the joint density of the portfolio that including two stocks and maybe some shorting on one of the stocks. But again, we are interested in the joint of u and the v. So what do we need, or to start from?
Do you need the inverse of x1 and x2?
So you want to solve the inverse first, right? Okay. So okay, so that means you want to go with J1 if you start from inverse. Okay, I see. Yeah, then maybe let's go from the inverse function first, the J1 first. Wait, with the H is the J1. Okay, but either way, it just gives you the same answer. So which way do you guys want to go with first?
So we go for G2, you don't need the inverse, right now?
Yes, actually that was what I was thinking originally.
Yeah.
So if you go with the J1, that means you need the inverse function. But the thing is that here you can see that the transformation is quite easy because it's just a sum and then minus. So maybe go with the J2 would be easier. So maybe how about we start from J2? Okay. So now let me write down collecting the information here. So what we have is U. So this is the G1 of x1 and x2. So now I'm just introducing the G and the H just to make for elaborating using how to use the formula. So U is equal to x1 plus x2. So back to the formula, that is essentially just the G1. Okay, so G1 is telling us this is just the sum of the x1 plus x2. Okay, and then for V, maybe let me use lowercase u. And then the V is, in terms of the formula, is the G2. And then the question giving is the x1 minus x2. So in the question, of course, it will not give you what is G1 and G2. But if you want to use the formula and then also for clarities, you can bring in the formula here. The U, the transformation is essentially just the G1. The V is essentially just the G2. But in the question, it just directly gives you the function there. Okay, and because we noticed that the G1 and G2 are quite simple, so we can start from J2. Yeah. So we don't need to worry about the inverse. But if the G1, G2 are quite difficult, then maybe you can try the inverse. Maybe the inverse will be easier. And then you can start from J1. Okay, so that's that. Then start from J2. J2 is saying we want to take the derivative of do you guys need me to write down the formula, or I can directly calculate the gradient, the derivatives here? Okay, maybe I'll just directly calculating that. So you can look up your notes on the formula. So for the 1 entry is the G1 with respect to x1. So G1 is this one. Now we take the derivative with respect to x1. What does that equal to? Okay, then let me write down again. So du dx1. Okay, so u is x1 plus x2. When I take derivative of the u with respect to x1, what does that equal to? Equal to 1, right? Yeah. Okay, so maybe let me provide some more steps then. Okay, so using the formula, the first row is the G1 with respect to dx1, dx2. The second row is the G2 with respect to dx1, dx2. Okay? And then we need to calculate the determinant. Okay, so now for the derivative of the u with respect to x1 is 1. What about the derivative of u with respect to x2? Should also be 1, right? What is the derivative of the v, the x1 minus x2, with respect to x1? 1, right? What is the derivative of the v, or the g2, with respect to x2? Negative 1, right? Yeah. Okay. Any question up to this point? So the formula for the J2 is the G1 with respect to x1, G1 with respect to x2, G2 with respect to x1, G2 with respect to x2. So G1 is x1 plus x2. Derivative with respect to x1, only going to affect on this term, you have a 1. With respect to x2, that's another 1. With respect to x1 for this one, that's a 1. But with respect to x2, there's a negative sign here, so a negative 1. Now you have the 2 by 2 matrix. Calculating its determinant. Determinant is the product of the diagonal minus the off diagonal. So you have 1 multiplied by negative 1 minus a, maybe I should also change the, so maybe this will be, okay, multiplied by 1. And what does that equal to? Negative 2, right? So J2 is equal to negative 2. Ah, I see. It seems like no matter what, you need the inverse function. Yeah. So later we'll calculate the inverse function. But first, the derivative of the Jacobian part is easier from the J2. So let's start from the J2. Okay. Any question up to this point regarding the Jacobian matrix, the derivatives, and then the determinant? Okay, so now back to the formula. We've taken care of the determinant part. Now we just need to handle the first part to rewrite this part in terms of the inverse function. So it seems like no matter what, you first need to, you still need the inverse function. Yeah. But whether G1 and H1 is easier will help you decide whether you want to start from J1 and J2. Okay. So now we finished on J2 on the Jacobian matrix part. Now we're going to focusing on the first part, the inverse function part. Okay. Okay. So the inverse function we are interested is something that you input u and the v, it will return to you x1. And then the second inverse function is also when you input the u and the v, it will return to the x2. Okay, so now the question is how to construct these inverse function. Okay. So now is that we want to come up with a function that can input u and v to get you to return only x1. And then you only input u and v and then only give you x2. That is the inverse function h1 and h2. Okay. So the way to get those usually it's just by sometimes it can be not very trivial, and it can be just like by trying things. So for example, we know, let me just write down, u is the sum of those, v is the difference. And keep in mind that, for example, for the h1 inverse, we want to find a function that input u and v and output x1 only. So we need to think about a way that I can separate the x1 alone. Okay, so one thing you can do that is through u plus v. Okay, so let's try u plus v. U is equal to x1 plus x2. V is equal to x1 minus x2. So you can see that when you sum the u plus v, you will get 2x1. Okay, so by doing the sum of the u and v, you have a way to separate x1 only, so the x2 disappear. Once you notice this relationship, you will have x1 equal to 1/2 of u plus v. And then this will be the inverse function h1. U and the v. Okay, so again, the inverse function is that you input u and v and get u x1. Okay, then let's think about how you can separate the x1 alone. And one way to separate x1 alone is by taking the sum of u plus v. You will be canceling out the x2. You only obtain x1. Moving the factor 1/2 in the front, you will obtain this relationship. And then this relationship is the inverse function. Input u and v only, output x1 only. So that is the inverse function. Any question up to this point? So the transformation is that you input the original, output the y1 and y2. You output the new things that you want to get. The inverse function is saying you input the transform items, you will get the original component, the x1, x2. Okay, so now let's think about what are some ways. So again, the inverse h2 is that you want to input the transform variables, u and v, but output x2 only. So what are some ways that I can separate or removing x1 from the picture, only keeping x2? So one way you can do that is by taking the difference of u and v. So u minus the v is x1 plus x2 minus x1 minus x2. you will have 2x2. Okay, so that is saying x2 is equal to 1/2 of u minus v. This is your h2. Maybe let me shift a little bit. So from the relationship of u plus v, we will get the inverse function for h2, h1. And then for the relationship for u minus v, we are able to remove the x1 out of the picture and then getting only the x2. Any question up to this point? Okay, now we have all the components needed. Now just go back to the formula. The joint density of the new component is equal to the density function of x1 and x2, but using the inverse. U and the v, and then h2, u and the v. And then because we use the Jacobian of we use the J2, so we will need to use the formula for J2, which is absolute value and then the inverse of that scalar. Okay, so now let's back to the density function of the x1 and x2. So here, what we need is the joint density function of x1 and x2. But because they are independent, so the question, or it tells us that x1 and x2 are independent. So the joint density function, okay, so maybe let me write it here. Because x1 independent of x2, the joint density function of x1 and at x2 is equal to f of x1 multiplying by f of x2. Okay, and this is also similar to our, if you still remember, the Buffon needles, where we drop the needles, the angle and the distance from the line is independent, so the joint density function is equal to the product of the margin. So again, before week 8 or week 9, we're all working on the margin. Okay, but now when we are ready to talk about more complicated things for decision making, such as the Rouse or the Stokes example, then we're talking about the joint. The joint either come from the conditional part, the A conditional on B multiplied by the margin of B. That is when they are conditional, not independent. But when they are independent, then you can make the product of the density function, of the individual margin. And if you still recall from week 1, our Buffon needle just fall into this regime. And our Buffon needle, the one that I'm motivating the whole course, is talking about the joint density function. Any question up to this point? Okay. So now let's figure out what is the joint for the x1 and x2. We know f of x1 exponential distribution. So we will have something like this. F of x2 negative x2 x, do I use x? Yeah, I use x1 and y x2. Okay, yeah. They are independent, so the joint x1 and x2 is equal to the product of the two. So you will have lambda 1 multiply by lambda 2 exponential of let me just write it in the same way here. So the E of the negative lambda 1 x1 plus lambda 2 x2. Okay, so the joint is just the product of the two. Any question up to this point? So it really depending on your preference. So I'll just break the parenthesis here by just writing the minus sign. So the minus of lambda 1 x1 minus lambda 2 x2. So the sum of the powers. Yeah. Okay, that's the joint of the original x1 and x2. But don't forget we need to transform through the inverse function. So the f of y1, y2 now we need to replace by the inverse function. So we have the lambda 1 multiplied by lambda 2 e. Okay, so maybe now let me write it as the exp, the negative lambda 1. So the idea is that whenever you see an original random variable, the x1, replaced by the inverse function. Okay? So now, when I'm just copying down, I encounter my first x1. When you see the original variables, replaced by the inverse function. This is what this is saying. Replace the x1 with this form, okay? And this form, again, the inverse function is saying input u and v, output x1. So replace x1 by the function of u and v. So the inverse function h1, we find out that is 1/2 u plus v. So whenever you see an x1, instead of writing x1, replace with the function of u and v. So the u and v in 1/2 describe the relationship of x1. So the density function of the new variables, instead of writing x1, writing with the relationship that can describe the x1. Okay? So x1 is 1/2 u plus v. Okay? x1 is 1/2 u plus v minus lambda 2 x2. So now we encounter the x2, go back to the inverse function. We find out the relationship for x2 is 1/2 u minus v. Instead of writing x2, writing with the relationship that describes the x2, 1/2 u minus v. 1/2 u minus v. Closing that. And now let me just ask you, does that complete the picture here? After replace with everything. We need a determinant, right? So one common thing is that, or from the past experience, people usually forget the J1 and J2 in the end. So always don't forget there's a J1 and J2, okay? And because we choose to use the J2, so using the formula of the J2. So J2 we got is, what is it? -2, okay? Formula for J2, -2, absolute value, and don't forget there's an inverse, okay? So even if you recall there's a J2, don't forget there's an inverse for J2. And absolute value of -2 is 2, inverse of that is 1/2, okay? So in the end, the final density function, lambda 1 multiplied by lambda 2 exponential of, how to write this more, okay, so maybe I'll put lambda 1 over 2 and then u plus v minus lambda 2 over 2 u minus a v, closing that. And then I will bring the I will bring the 1 over 2 maybe in the front, okay? Or you can write lambda 1, lambda 2 over 2. Okay, so that is your joint density function of the new, I shouldn't write, so in this example, instead of y1, y2, I use the letter u and the v, so let me replace. So this is u and the v, and then u and the v, yeah. y1 and y2 is generic letters for the formula, but in this problem, I'm using u and v, so this is the function of u and v. So again, this is the final density function for the new random variable u and the v. So you can see that on the right-hand side, no more x and y, no more x1 and x2 showing up. You only have u and v. So this is a density function that describes the relationship of u and the v jointly. And then if you want to calculate probability of those things using this density function, using integrals for the probability problems. So again, probability always come after you have the density function. And throughout the lecture, I'm providing you lots of ways to manipulate the density function. Once you have a density function, you can calculate the probability accordingly. Okay. Any question up to this point?
Can you assume these are continuous?
Yes. Because we start from x1 and x2 exponential, so they are exponential, so continuous. So kind of depending on where you start with. Yeah. That's a good question. Any other question or comments?
So what
Yeah.
was like the underlying motivation behind this?
Is that still like the like the traveling time problem, let's say, because that is relatively easier to think, is that if I have 2 points and then the company was asking you go from route A or go from route B. So in the practice midterm, I was asking you what is the difference between x and y, right? And then if the probability is quite large, you can decide that you probably want to discard route A, you want to go from route B, right? So that is a single variable. So you use the moment function to get the density function, right? You notice that's a normal, and then you calculate probability, right? But that is single variable. But what if your company is asking you, what about D1 is the difference, but D2 is the sum? Let's say I want to travel and then coming back from the route. So that means I use both of them. Then the variability, so the variations is including the random variable x and the y, and x plus y, because I use both routes. And then that is my D2. So I was asking you, what is the density function for jointly D1 and the D2? So something that can describe both behaviors. Yeah.
Okay.
Yeah. But whether this one is meaningful or not, depending on the question in practice. Like maybe the question will be interested in both of them, and then you can calculate the probability of that. So maybe the company may ask, what is the probability that if the differences is less than 5, but the total sum is still within less than 20 minutes. So route A more than route 2, more than 2 minutes, but the sum I can still manage on 20 minutes, then you would need the joint density function. To calculate the joint density, to answer that question, you will need double integral f of d1, d2, d1, d2. So d1 less than 2 minutes. So that is saying the difference of the two routes, I need to manage on the less than 2 minutes. So if they are not normal distribution, -2 up to 2 for the inner integral. For the outer integral, let's say I want to manage the sum of the two routes is within 20 minutes, then it's -∞ to 20. You need to calculate, so if you want to answer that business problem, the first thing you need to get is the density function of that. And what I introduced today is that how you can get the density function of that, given that you only know the route 1 and route 2 following normal distribution. Yeah, but the business question is not only x1 and x2, it's talking about the difference of x1 and x2 and the sum of x1 and x2. And then you need a density function to answer that probability question. So what I introduced today is the first step, how you get this one. When you know your business is interested in the difference and the sum of that. Does that answer your question?
Yeah, that's good.
Yeah. So, yeah, to answer a probability question, we need the density function. To get the density function, we need lots of transformation thing to get those.
How do you know which one's the inner integral and which one's the outer?
Right now, it doesn't matter at this point because they are independent, they're not dependent. But when they are dependent, usually you will write the things that are more dependent in the inner one and then solving the one more independent or more unrelated one on the outside. Because because that one depending on that one. So you will need this more dependent thing in here. But that is even complex. That is the dependent thing. Right now I'm assuming they're independent, so you have this simple scenario. Yeah. But for your case it's even complicated. You will need more inner thing. So the idea is to put it in the inner integral.
But if it's independent, the order doesn't.
Doesn't matter because in that case you will have like let's say 20 minus d1. So you will need the d1 inside the integral. So for an independent case it doesn't matter. Yeah, that's also a good question. So now we're just providing you more tools to calculating, to handling more difficult cases. Yeah, the joint case. And the even difficult case will be other than 2, you can have 3 or more. That would be more complicated. And then if you want to make it more complicated, you can make them dependent. x1 dependent on x2, x3 and 5, and then some of them they're dependent. Then the joint density function is even complicated.
So this was about like deriving a joint case
Density, yes.
given two independent random variables.
In this context,
Yeah, in
yes.
this context.
Yes, yes. So, yeah, the things that we collect is like we collect patient data. But what we are not interested in is the direct patient. We are interested in what is the average of the patient. Then that is the sum, right? The sum of the patients and then taking the average. Yeah. So the data we collect may not be the business question that we're directly interested in. We need some transformation of that. Then we need to take the average or take the sum, take the difference. Because average is also a sum, right? Scaled by 1/n. Okay, I can pause here, or if you guys are interested in another question, in another example, but I'm not sure if I can finish that. That's a relatively long one. What do you guys want? Maybe I'll save it for next week? Yeah. Okay, I'll pause here.